Hi everyone. Today we're going to be talking about the behavior of light. So, in the past, we have been talking about how we can model different processes within science. And we have two different types of models that we can use when it comes to light. One is the wave model, which is what we've been using to show the property of light and their characteristics. So properties and characteristics are talking about the amplitude, the wavelength, the frequency, the energy. The wave model allows us to see all of these in a nice snapshot. What it doesn't show us is how light behaves. So we use the ray model. We talk about how it behaves, we're talking about it's mostly the direction that it's traveling. So a ray model is used to show how light behaves when it moves through different mediums. A medium is, an example, water, air, outer space. So any medium is a substance as it's moving through a substance. So here we have our two different diagrams. We have a wave model, which we have been looking at throughout this unit. And now we're going to add another type of model called the ray model. I want you to draw those two diagrams on your notes. So wave model, it shows the properties, the characteristics, wavelength, amplitude, frequency. The ray model is going to show us the direction that it's traveling. So let's get into it. So light waves will always travel in a straight line and take the shortest possible path. So straight line and take the shortest path possible. We use a line with an arrowhead to show the direction that light is going to travel, and this is known as a ray. So here are some different models showing how light is going to travel. Notice there's no zigzags within those rays. They're always traveling in a straight path. Some are changing direction or the angle that they are moving at, but overall they're traveling in a straight path. No zigzags, jagged edges, curves, loops, just straight lines. So there's two different ways that we know light can behave. One is reflection, and that's when a wave strikes an object or a surface and it bounces off. A mirror. When you're looking in a mirror, you see your reflection. That's what's happening with the light. The light is striking the mirror, bouncing off, going towards your face, bouncing off of your face, going back towards the mirror. It's continuing to move between you and the mirror and allowing you to see it. Same with this beautiful image, the mountain and the lake. That surface is smooth enough that it's allowing that reflection. So one of the main principles of reflection is the law of reflection. And this states that the angle light hits a surface is equal to the angle that light is reflected off. We can see in our image, we are using a mirror as the surface. So light is traveling in a straight direction. We know it is traveling towards the mirror because of the arrowhead. So the light coming towards the mirror, it is then reflecting or bouncing off and changing direction. Our arrowhead tells us this is the light that is bouncing off. These two angles, and I'll talk about what this line is in a moment, but these two angles are equal to each other. So let's talk about the parts of the model, what we had just seen. We have the incident ray, and this is the light that's approaching a mirror or a surface. We know that this is the approaching ray because this one, the ray is bouncing off. So we call this the incident ray, the incoming light. The arrow, the ray that is bouncing off of the mirror, is the reflected ray. So the reflected ray is the light that bounces off the mirror. That is the outgoing light ray. Next, we have the normal. That is what this dotted line is. And what we do is it's an imaginary line. It's not light. It's just an imaginary line that we draw perpendicular, or 90 degrees, to the surface of the mirror. And that normal line is what we use to see how the light is reflecting or refracting, as you know from reading. So the normal separates the angles between the incident ray and reflected ray. So the normal is separating these two angles. So what do we call them? Well, the first one is the angle of incidence. It's the angle between the incident ray and the normal. So the angle of incidence is between the incident ray and normal. Then we have the angle of reflection, which is just the angle between the reflected ray and the normal. The law of reflection tells me those angles are equal to each other. No matter how the light is incoming, it's going to be bouncing off at the same angle. All right, little checkpoint. I want you to take a moment and I want you to label the diagram in your notes using the 5 vocab terms previously discussed. So go ahead, pause the video. Did you pause the video? Did you try it on your own? All right, let's check our answers. So incident ray coming in, reflected, bouncing off, normal, that 90-degree perpendicular line, angle of incident between incident ray and normal, angle of reflection between normal and reflected ray. Take a moment to pause the video if you need to add anything to your paper. Otherwise, we're going to move on to refraction. So refraction is when the path of a light wave bends as it passes across a boundary separating two different mediums. Remember, mediums are just substances. And this is caused by a change in the speed experienced by a wave when it moves through medium of different densities. Recall, density is how tightly packed substance, the particles within a substance are. Density is the amount of stuff per space. The closer particles are together, the more dense they are, compared to particles that are a little bit farther apart. Those are less dense. For example, glass is more dense than air. In glass, the particles are really, really, really tightly packed. That's why you can't easily put your hand through it like you can with air. Air, the particles are really far apart, so we're able to move through them. Yes, they're two different states of matter, but just roll with the analogy. So when a light wave is reflected, the light ray changes direction. So as it is refracted, it changes direction. I have a really good analogy to think about what is happening. So here we can see that the speed is changing when it's refracting, and that's going to cause it to change direction. No? We'll get there. All right. So the main idea is it has to be passing through media of different densities. So when we're moving from an area with a high density to a lower density, think about it when you're moving from the sand to the pavement, you're going to start to speed up. You're going to move quicker. What happens with light is light speeds up, and it's going to actually bend away from the normal because the incoming angle is traveling at slower. And then once it hits the boundary, it starts to speed up and it shoots off to the side away from the normal. It's able to speed up much more quickly. So think of this as you are going from sand to cement. You're able to speed up, you move much more quickly, and you zoom off. Now it's the opposite if you go from low density to high density. So when you're going from the pavement to the sand, the light slows down and it's going to bend towards the normal. So it's slowing down. It's not zooming off very quickly. It's slowing down. It's taking its time. It's getting closer to normal. So one example can be going from air to glass. Let's model it. So when we have refraction, we still have an incident ray, that incoming light that's approaching a boundary. The big thing with refraction is you have to have two different densities. Keep that in mind. Two different densities that it's passing through. So the incident ray is the light approaching the boundary. The refracted ray is the light that crosses over the boundary. In this angle is going to change based on the density it's moving into. We then have our normal, just as before. We have that imaginary line drawn perpendicular, or 90 degrees to the surface of the mirror. We know the normal separates the, I have a spelling error right there. That should be the refracted ray. Sorry about that. So the normal line separates the angle between the incident ray and the refracted ray. Whew, that's looking a little rough. Thankfully, you don't have to fill those on your line. You just have to say the normal line separates the angle between the incident ray and refracted ray. Oh, it's right on your notes, but not in the slides. Interesting. Funny story. We're going to roll with it. Angle of incidence, just as before, it's the angle between the incident ray and the normal, so that does not change. What is different now is we know it's not bouncing off, it's moving through the medium. It's going to be changing its angle because the speed is going to either increase or decrease, so that is called our angle of refraction. The angle of refraction helps us know which medium is more dense, because if it's moving towards or away the normal, speeding up or slowing down. All right, I want you to take a moment, pause the video, and label the sections of the refracted ray, the refraction model. All right, I'm trusting that you had paused it, taken your time. Here we have, again, incident ray is the incoming. Refracted is the ray that moved through the medium after the boundary. Angle of incidence, angle of refraction, and of course, our normal. Pause the video if you have to add anything to your diagram. Otherwise, you're going to be completing the check-in behavior of light. It should be posted in a little while. Bye, friends.